Hello and welcome to our presentation. We are the nanopaper team, Tuukka, Virkki and Paul Lim, and we're here to tell you about our project on nanopaper. We have been studying the effects of pressure and airflow on the drying rate of nanopaper, and we're doing this in collaboration with the Bioproduct Center of Aalto University. Let's start the presentation with some basics of the topic. Some of you might be wondering what nanopaper is. Well, to put it simply, nanopaper is just like normal paper, but built from smaller fibers. Paper is produced from a pulp that contains water and wood fibers. The paper sheet is formed by pressing water out of this pulp until there are only fibers left to form a sheet. Traditional paper is made from large fibers. With the nanopaper though, the wood fibers are processed to nanoscale by grinding. So the fibers left in the pulp are much smaller than the normal paper fibers. When the water is pushed out of nanopulp, the paper that is left is much more dense. Many studies have been conducted on nanopaper recently. This is because researchers believe that nanopaper has great potential and many applications in different fields in the future. The reason we believe there is great potential in nanopaper is because of its unique properties. These properties include, for example, great tensile strength and conductivity. And as we can see on the picture on the right, nanopaper can also be transparent. With these properties, it could be used in various applications. It could, for example, be used to replace oil-based products like plastic packaging. There are also applications in electronics and biomedical field because of the conductivity and biodegradability. Nanopaper is also a sustainable material because the raw material can be obtained from agricultural waste. Okay, well, why are we not using this great potential and properties already? There are still many challenges in commercializing nanopaper. Because of the smaller fiber size compared to normal paper pulp, more energy is needed to dewater the pulp and dry nanopaper. Because of the energy consumption, the scalability of production is still not yet figured out, and the price of nanopaper is not on par with normal paper. The dewatering and drying process must be researched to enable commercial production at some point. And with this small introduction, we'll now move on to what we have been doing in our project.
As mentioned before, the project was done in collaboration with the Bioproduct Center of Aalto University, and our objective here was to see how pressure and airflow affect the drying rate of the formed paper. To do this, the group had to design an airtight device that would be under pressure and possibly be exposed to boiling temperatures. It was also requested that the chambers would be transparent in order to see the process of paper forming more clearly. As for the device itself, it is rather modular, meaning we can add different sensors, change the filter plate, and add more components. This gives the device more value because building the device is only one step of our project. Gaining data on how nanopaper dries under pressure was the purpose of building the device. The modularity of the device allows us, for example, to research how temperature would affect the drying rate once the necessary sensors and components are added. The process is done in two phases. The first phase focuses on producing the paper sheet on top of the filter plate. This is done with the help of pressure, which forces the water from the upper chamber to the lower. The only thing left is the wet paper sheet on top of the filter plate. After the first phase, we remove the water from the bottom chamber, wipe the chambers, and weight the filter plate that holds the paper sheet and place it back. On the second phase, we increase the pressure and add a vacuum on the bottom chamber. This is also when we start taking measurements of pressure and airflow. The second phase is kept going for a couple of minutes before we turn off the pressure valve. After the second phase, we take the filter plate out and weight it again. The difference in weight tells us how much the paper dried. Next, we will show you a video that visualizes the first phase of our process.
Alright, hi everyone. My name is Tuukka Virkki and this is my colleague Po Lim. We're going to introduce you to our nanopaper process and the device. So here we have our nanopaper device, which we built. On the top here we have our pressure regulator, our pressure sensor, our pulp, and our flanges that contain the filter plate. And on the bottom we have our draining system. So now we have our power supply connected to our pressure controller, and next my colleague is going to give out a signal to the controller, and we will increase the pressure inside of this chamber. This leads to the water going down to the next chamber and through the filter plate. When we increase the voltage, the controller allows us to have pressure in the first chamber. Next, we apply pressure to the chamber.
After all the water has drained, we can disconnect the middle flanges and take out the filter plate with the paper sheet.
This was the first step of our drying process, and in the end you could see the wet paper sheet that was formed. This wet paper sheet still needs to be dried, and that happens in the second phase with the help of increased pressure and airflow. In the video, we conducted a test run of the process with normal paper. For phase 2, we set the pressure to 2 bars while the lower chamber valve was open. The paper dried completely in 5 minutes. Our future plans are to add an air heater so we can also study the effects of temperature of the drying process. And to give you the faces behind this project and presentation, here's a picture of our team. And here are the sources we use for the figures. Thank you, the audience, for taking your time to listen, and we would also like to thank the Aalto staff for helping us with the project.